Yeah, today we are going to discuss about the chapter 7, diffusion, which part of our fundamental energy material courses. Yeah, let's begin outline. The key question we will address is in this chapter. First, how does the diffusion occur at the atomic level? Yeah, second, why is diffusion an important part of the material processing? Yeah, next is how can we predict the rate of the diffusion for the simple cases? And finally, how does the diffusion depends on the structure and temperature? Yeah, in the previous lecture, we discussed the imperfection in the solid. Today, we will focus on the diffusion. Diffusion describes the movement of the material. In our department, since we frequently deal with the summer phenomena, we will like to make a concentration to heat transfer. However, it is important to understand that before heat can transfer, mass must be moved first. This is why this is often called mass transportation, and diffusion is an aspect related to the mass transportation. Understanding this concept will help for you in these courses, and later you will take courses Professor Kim Shin heat transfer classes. You are already familiar with the diffusion from the everyday experience when you drop ink into the water and the ink droplet gradually spread. This is a classical example of the diffusion. While we understood it that way when we were young, now we need to think about it from the atomic perspective in terms of energy fundamental. What is actually happening? Atoms are moving, but atoms move and several conditions must be met. Let's explore how it occurs. So, diffusion is anyway mass transportation, movement of the material through the atomic scale motion. The mechanism effectively by best. In the gases and liquid, atoms move randomly, the following we call the Brownian motion. In solid, atom need to available space to move. This occurs through the Bacon's diffusion, where atoms move into the Bacon's lattice site, or through the interstitial diffusion, where small atoms move the gradually atomic position. Yeah, let's discuss interdiffusion in more detail. We previously introduced the concept of the alloy. When two different metals combine, they form alloy bond. This typically occurred between the similar metal elements such as copper and nickel. How is the material actually mixed? Consider the simplest case. When you join two different material A and B, initially one side is 100 element A and the other side is 100% element B. With this concentration difference, atoms naturally tend to migrate from high concentration to the concentration region to the low concentration region. These driving forces cause the atom to move across the interfaces. The high concentration site become diluent, while the low concentration site become enriched. Given sufficient time, long time, the system reached the equilibrium with the uniform composition. Throughout, they become half and half. However, this is only occurred when elements can form solid solution. When they are similar enough to mixes, if the elements are incompatible, for example, in one is much larger than the other, and sharp interfaces will remain instead. For competitive element, this intermixing happen spontaneously just by putting them in contact. However, at room temperature, it needs to wait several decades for the significant mixing happen. In practically, this processing requires elevating temperature, such as welding or something. Welding is also need the raising the temperature to melting interfaces or allowing solid solution formation to occur rapidly. Yeah, now let's example self-diffusion. Diffusion in the pure element containing only one type of the atom. When we label individual atom A, B, C, D looks like this, and then observe them over the time, you will see they move to the different position looks like this. This reveals an important insight. Although a solid appears stationary and maintains its shapes, but atoms are continuously moving internally to maintain that structure. At very low temperature, these atomic movements become rare, essentially negligible. But at the high temperature, self-diffusion becomes significant. Yeah, next, let me explain the Bacon's diffusion mechanism in more detail. Bacon's diffusion atom exchange position, Bacon's lattice site. This mechanism applied primarily to substitutional impurity atoms. For this occurred, Bacon's defect must be exist in the crystal structure. On atom adjacent to Bacon's can jump into the Bacon's site. The late Bacon's diffusion depending on the two key factors. First is the number of the Bacon's presence. More Bacons means the faster diffusion. And then second, activation energy required for atom to jump into the Bacon's site. As you can see in the animation, the atom progressively moved into the neighboring Bacon's site and creating the continuously diffusion path through the material. This mechanism is conceptually straightforward, I think. Yeah, actually we can simulate the diffusion process computationally. I'm going to explain those kind of detailed example in the offline classes that I'm going to skip it. Next is interstitial diffusion, where smaller atoms move between the spaces of the large host atom. For interstitial diffusion occur, the diffusion atom must be small enough to fit into the interstitial site. Looks like this. When moving from one interstitial site to the another, atom must be overcome the energy barrier. The slide mentioned that modified Bacon's diffusion, but this terminology varies depending on the context. Interstitial diffusion can be faster than Bacon's diffusion when atoms are very small. However, it's not always faster because that the formation energy for the interstitial defect is typically much bigger than for the Bacon's site. Remember from our earlier discussion that diffusion rate depending on the concentration of the defect, even if the migration barrier is lower for interstitial cases. If very few interstitial sites can be occupied, overall diffusion may be still slower than Bacon's diffusion. However, that when atoms are truly small, like we learned when discussing carbon in iron, both interstitial formation and migration energy barrier can be low, enabling very rapid diffusion. The most prominent application of this is case hardening. Case hardening is the surface treatment process for the iron component. When the casting iron compound, it is beneficial to adding carbon near the surfaces. How is this done? Traditionally, iron castings are heated until red hot, and then carbon powder is sprinkled on the surfaces. The high temperature allows the carbon atom to rapidly diffuse interstitially into the iron site. You can see the surfaces has a different color when carbon diffusion into this in the carbon enriched layer. As discussed previously, the carbon atom act some obstacle to dislocation motion, like a speed bump. They increase the activation energy for slip. So to preventing the dislocation movement. So when applied case hardening in the iron material, the dramatically improved mechanical strengths and wear resistance we obtain. I prepared some video example demonstrated of this process. Please so watching that movie individually, but please don't try this at home. It involved very high temperature and can be dangerous. The processing, so when after watching this video, you can know that the processing use oil, which contains a hydrocarbon, carbon-rich molecule. At the high temperature, these decompose and carbon diffuse into the iron surface. A carbon-based material, oil in this case, is that through the exact composition varies, provide the carbon sources. The key principle is ancient, faster carbon diffusion produce the better cases hardening and stronger mechanical property. This has been known since the ancient time, so you can follow the easier. And next is semiconductor doping. Another critical application of diffusion is semiconductor doping, used in the solar cell or integrated circuit. We doped silicon to create the P-type or N-type semiconductor. The doping process lies heavily on the diffusion. Here is the work processing. First, we dope the phosphated rich layer on the silicon surfaces in the specific pattern. This deposition method is itself involved various complexes process. Second, we hit the vapor. This is crucial because that the vacancy concentration in the silicon increased with temperature. Remember that vacancy move outward from the bulk. So conversely, phosphorus atom can diffusion inward. By patterning the phosphorus layer, we control the where doping occurred. Through the thermal diffusion, phosphorus penetrated into the silicon, creating the doping region, essentially, for the semiconductor devices operation. Since we discussed semiconductor, I should explain the fabrication of this process. So, semiconductor started with the sand. I'm going to skip it. Few seconds. Semiconductor started with sand, silicon dioxide. We apply the intense heat for purification and solidification. Critically, we must produce the single crystal vapor, not polycrystalline material. This is not an easy process. Once we have silicon vapor, they undergo numerous processing steps. For patterning, we use photoresistive process. A pattern mask is illuminated with UV light through the lens, projecting the microscopic pattern on the photoresistive coating vapor. After developing the photoresistive and etching, we created a pattern where masked region remains protective while unmasked region are etched away. This process repeated many times, building up complex three-dimensional structure layer by layer. The ultimate goal is to create the conductive pathway that carried current only under specific voltage condition. That is the essential of the semiconductor devices operation. Each unit cell extracted from these pattern vapor become functionally semiconductor devices. High yield means producing many working devices from each vapor. When I first prepared this video, Intel company was undisputed leader in the semiconductor manufacturing. However, recently Intel has stopped the back for the leading edge processing, with Taiwan TSMC now dominating. Samsung Electronics in Korea is also established the foundry operation in Pyeongtaek, and this sector continuously to expanded rapidly, I think. Yeah, both design and processing are important. Throughout this process, diffusion-based doping is fundamental. I hope that someday we can update this video to highlight Samsung's achievement alongside TSMC. Yeah, this is the end of the movie. Yeah, now let's discuss about how we quantify the diffusion rate. Yeah, we defined flux J. Yeah, mass diffusion per unit area per unit time. Mathematically, J equal to the moles or mass M and divided by the cross-section area and time. This is analogically to fluid flow, which also use the amount of per unit area per time. How do we measure the flux experimentally? We created the thin film membrane, non-cross-section area, established the concentration gradient across it, and then measure the how rapidly atom or molecule diffusion through it. By plotting the mass diffusion barriers versus time, we obtain the flux from the slope. This flux is proportional to this slope, maybe. Yeah, so let's examine steady state diffusion, where the diffusion rate is independent of the time. The flux remains constant. Under steady state condition, flux is proportional to the concentration gradient. This is a first fixed law. J is equal to the minus D and concentration gradient. The negative sign indicates that diffusion occurred from high to low concentration opposite to the concentration increasing direction. So when concentration profile is linear, we can approximately dx/dc is equal to those kind of finite difference of the concentration changing. The diffusion coefficient D characterized how easily atom diffusion through the material. Large D means that high D flux, small d means that low fluxes. So here's a practical example. Methylene chlorine is commonly used paint remover and nail polishing remover. It is an irritant that can be observed through the skin, so the protective gloves are essential. If we use the butylene rubber gloves, 0.05 centimeter thick, what is diffusion fluxes of methylene carbonate through the glove? Yeah, given data, diffusion coefficient D is the 110 10 to the minus centimeter square per second. Paint remover side concentration C1 is 0.44 gram per cc and skin side C2 is the 0.02 gram per cc. Global thickness, I already told it, 0.04 centimeter thick. Applying pixel law assumption, linear concentration gradient, you guys can calculate it here. So we value finally that this revealed that the globe does not provide perfect protection. Methylene chloride continuously diffusion through the skin surface at this rate to maintain assumption skin surfaces concentration 0.02 gram per cc. Your skin must continuously absorb the methylene chloride at these fluxes. Without glove, 100% would contact your skin directly, so the glove provides significantly safety, but not complete protection. And next is temperature dependent diffusion. Diffusion is strongly temperature dependent. Diffusion coefficient increased exponentially with the temperature according to those kind of Arrhenius relationship. D is a diffusion coefficient, D0 is a pre-exponential term, QD, you guys familiar with this is activation energy, and R is gas constant. But when you're changing gas constant, the Boltzmann constant, and then you guys familiar with this RT or KD has a similar value of the unit energy. This equation is also similar to the we show for the vacancy concentration. The difference is in the unit, simply. The key point is that diffusion coefficient varies exponentially with temperature. Small temperature changing can dramatically affect the diffusion rate. This graph demonstrated the exponential temperature dependence of the D. Plotting D with the logarithm versus inverse temperature yields a straight line, making it easy to extract the activation energy from the slope. Notice that the interstitial diffusion is slightly faster than substitutional diffusion. The interstitial example alpha carbon in the alpha iron and carbon in the gamma iron. Substitutional cases that aluminum in the aluminum, or this is a self-diffusion actually. Iron in alpha iron or alpha, those kind of is also the self-diffusion. However, they remember that the interstitial diffusion is not always faster. If the interstitial formation energy is very high, overall diffusion may be slower despite the lower migration energy barrier or activation energy barrier, because that so few interstitial sites occur inside material. Yeah, let's work through the example. At 300 Celsius, the diffusion coefficient of the copper in silicon is about this value. With the activation energy 41.5 kilojoule per mole. Yeah, the question is the calculated diffusion coefficient at 350 Celsius. We use the relationship between the D at two temperature, taking the natural logarithm of the Arrhenius equation. Both temperature substitution looks like this, and then converting the Celsius to the Kelvin, and then solving the D. Yeah, you can obtain, after 300 become 573 Kelvin, maybe 350 become 623 maybe. So let's do this more, so that finally that we obtain the D2 value is almost 15.7 10 to the minus 11 meter square per second. Yeah, notice that the 50 Celsius increase nearly doubled at diffusion coefficient. Yeah, this demonstrated that the strong exponential temperature dependency of the diffusion. You guys can feel it. Now let's discuss about the non-steady state diffusion, where concentration varies with the both position at the time. For these cases that we use the Fick-second law equation. This equation derived from the mass conservation. It started that the rate of the concentration changing equal to the difference changing equal to the diffusion coefficient time to the second partial derivative of concentration. Yeah, so this is the same form as the heat equation in the thermal analysis, just with the concentration instead of the temperature. The mathematically structure is identical actually. So why understanding diffusion help with the heat transfer or vice versa? But however, that we do not learn yet both the diffusion and heat transfer yet. But just remember it. Consider some scenario. Diffusion into the aluminum bar with the pre-existence copper concentration C0. Throughout the bar, we maintain the constant surface concentration Cs at x equal to 0 position. This is a mathematical boundary condition. After the t goes by, the surface concentration is kept constant, but the all concentration is slightly will varying. The concentration profile shows how copper penetrated deeper into the aluminum over the time. Initially, that there is a step changing at the surfaces at the time progress T1, T2, T3. The profile become progressively smoother and extended deeper. This is an example of the solid solution. However, that analytical solution, the Fick-second law with this boundary condition is too complex. The solution obtained looks like this. ERF is the error function, maybe that expresses those kind of integration formula. Maybe that we have some value in the table chapter 7. This solution tells us that concentration at any position at time during the diffusion processes. While the error function looks complex, it well tabulated, the making calculation straightforward actually. Yeah, here's a comprehensive problem. FCC iron carbide alloying initially containing a 0.2 weight fraction of the carbon. During the elevation temperature, the surface concentration maintainly 1.0 weight percent. After the 49.5 hours, the carbon concentration is about the 0.35 weight fraction. At the position is 4 millimeter depth. Determine the treatment temperature. Here that we already have some solution, but without the table we cannot obtain it. But however, please do this. T is the 49.5 hours, and the CX and C0 and CS looks like this. After put this value in here, but the right hand side is almost the 0.915. In the table that we can do the linear interpolation to obtain this value, and then we can put here to this, and then finally diffusion coefficient can be observed looks like this. And then finally that we can do here more, that to solve for the temperature at the where D has above the value. So from here that the D0 is from table, and the activation energy is expressed the joule per mole, and then finally temperature could be calculated almost 1300 Kelvin maybe. This is some example. Anyway, so let's revisit the methylene chloride example with the temperature different question. What is the break time? How long until methylene chloride reach the skin? For simplicity estimation, we use some equation. Maybe here, TB is equal to the 6D over the L square. L is the membrane thicknesses, and D is the diffusion coefficient of the globe and methylene chloride in the globe. And this relationship comes from the dimensional analysis. The factor of the 6 arises because the diffusion occurred isotropically in the three-dimensional spaces. And from the mathematically of the second derivative factor of E. And then 3 comes from the three-dimensional. For our globes, that the TB is looks like this, that almost 4 minutes. The globe provides protection for approximately 4 minutes. This is a conservative estimated the actual breaking time, maybe longer than due to the concentration gradient effect. However, that this provides the practical design guideline. When working with the paint remover, globe should be changing every 4 minutes for safety. This is not the most accurate method for the precision calculation. You'd solve the diffusion equation numerically with the boundary condition. The skin surface's concentration first exceeds 0. But this hand calculation gives a robust and conservative estimation. Anyway, last is a summary. Let me summarize the factor affecting the diffusion rate. The diffusion is the best for example, that open crystal structure. It is because they have more spaces for the atomic movement. And then last one, material with the secondary bonding, weak bonding and easier breaking. And smaller diffusion atom fit through the interstitial spaces easily. Lower dense material. Yeah, this is also can be generated or shows the more free volume available. Diffusion is slow for, such as a closed pack structure, less spaces for the atom to move. And the material with covalent bond, strong directional bond resist the breaking. Larger diffusion atom can fit through the space easily. Higher dense material, generated less free volume. Understanding this principle help predict and control the diffusion in the material processing. That's the conclusion today, the lecture of the diffusion. Since I went over the time last classes about almost 80 minutes, I trying to move through this material more effectively today. So we are close to 2 hours total, I think. Maybe, next lecture. So we've converted the fundamental diffusion mechanism, fixed first and second law, and practical application including the cases hardening and semiconductor doping. The key takeaway is the diffusion is atomic scale mass transportation that is crucial for many material processing techniques. However, remember that not only all material combinations follow this diffusion physics. When the incompatible materials are joined, they may not intermix even with the heating. In these cases, different physics model mathematical description are needed. The diffusion principle was discussed today, applied when materials are compatible, when Bacon's diffusion and self-diffusion and interstitial diffusion can occur readily between the similar elements. Next time we will return to the mechanical property, and please watching the movie continue about the chapter 8 of the metal and examine how crystal structure affected the mechanical behavior. Thank you for your attention today.